All right, so we'll go ahead and get started. I have some opening just information, and then I'll hand it over to Scott. So to introduce myself, my name is James Grant. I'm the Customer Success Manager here at iMeasureU. For those of you who don't know what iMeasureU is we offer a lower limb monitoring solution that takes the guesswork out of your load monitoring and return to play protocols. Some really quick housekeeping. We will have time for questions at the end. So at the bottom of the Zoom window, you should see a Q&A option. So if you have any questions for Scott that you want him to answer at the end of the webinar, throw them in there and we'll select a few and answer those at the end. We are recording this, so if you have to leave early, we will send you the recording afterwards and then this is the first webinar in our series. So if you want to stay up to date with the latest webinars, make sure that you sign up for our newsletter at iMeasureU.com, and we'll make sure that we let you know about any webinars coming up. All right, so let me introduce Scott McLean. Scott McLean is the Senior Biomechanics Manager within Exponent. There he leads a large-scale wearable technology initiative. In this role, he uses a wide variety of wearable technologies to support human performance and human product interaction optimization. His expertise lies in synthesizing and distilling the vast amounts of data generated through these technologies and putting them into the adjustable and translatable metrics that he uses to inform performance success. Before his role at Exponent, he was the Innovation Director at Fitbit and a professor at the University of Michigan. So without further ado, I'll hand it over to Scott and let him take it away.
Thanks, James. Thanks, everyone. Hope everyone is staying safe at the moment. I know it's a strange time, so this is an interesting way of presenting, so hopefully it gives some people some useful information and also helps to sort of pass the day. I wanted to, first of all, give a very brief outline about what my company is. So Exponent, we're basically a multidisciplinary consulting firm, engineering and scientific. It brings together more than 90 different disciplines: engineering, scientific, regulatory, and business issues. We are a global company. We have offices internationally. And as James said, so my area of focus in the biomechanics practice is primarily in wearable technology. And that goes anywhere from supporting wearable technology companies as they progress from startup through to large scale. But additionally, and a lot of that work involves utilizing current technologies, often integrated together in different sort of technology suites, as a way to inform a human performance optimization or risk mitigation, but also product support and development innovation. And through the presentation today, I wanted to I'll touch on those things to give context to the way that we use these different technologies. I've worked in parallel with iMeasureU and James and Blake for quite a while. We've used the technology quite regularly. We find it's a pretty optimal technology for some of the things that we do, and I'll show you that in the presentation today. The way we tend to approach these sorts of things is that companies such as iMeasureU are definitely like the technical experts, and we view ourselves on the back end as more the data experts that help companies and clients in, once they have these technologies in-house, being able to design studies and experiments or protocols to really get the most out of the technology, and also then in parallel develop a lot of the data frameworks that go along with that to provide those metrics that make use in terms of what the client needs are. So very briefly, in terms of my background, so as James touched on, I was previously Innovation Director at Fitbit. I was a professor at U of M. I was also at the Cleveland Clinic for around about 8 years, where I worked there with a couple of the pro teams at a sort of low-level consulting as a biomechanist then. Obviously, a lot of my focus on my research primarily was in orthopedic biomechanics, primarily in lower limb, where I used a vast array of sort of technologies and concepts and methods as a way to better understand injury risk prevention or risk sort of injury mechanisms and how to improve or mitigate against those using, as I said, various technologies, including sensor-based work. That was both in sort of athletic populations where we started to jump into wearable tech. So as that sort of research evolved, we moved out of the lab setting and more into the wearable tech space. And I think the primary rationale behind that is that, quite often, and I'll talk more about this in a moment, is that, you know, you can gain a lot of unique and very critical insights into performance in these naturalistic settings that are really sometimes harder to get in a lab space. And so we really pushed that direction to do so. And we had a lot of application in the sports sector, and obviously also, as you can see from this slide, in clinical sectors where we really use wearable tech to really improve sort of clinical methods and protocols. So one of the areas that we primarily or initially focused on with wearable tech was in the warfighter space, in the military space, where we developed and implemented basically an integrated wearable sensor suite that with the intent of being able to quantify explicit warfighter performance metrics in the battlefield. Now that can obviously be particularly challenging because if you think about warfighter performance, it's usually in extreme scenarios and often very sort of remote locations. But so this was a fun challenge, but definitely again, you can see where wearable technologies really will allow you to glean a lot of very important insights into what I would view as very critical performance metrics that you should and need to address. And the military is a great example. And some of the things that they do in the military space are obviously incredibly difficult to replicate successfully in a lab setting. So with that work, we did a lot of things from looking at monitoring performance degradation, looking at specific interactions between the warfighter and equipment, which I'll show you a little bit as an example in a moment. We use this a lot as an intent or a goal of basically being able for the Army, the military, to use this to make direct comparisons in body armor. So being able to understand and appreciate subtle differences in body armor and how they may impact performance. And this was what I viewed as probably the first step in towards our multi-state sort of sensor fusion model, which I'm going to talk a lot more about today, where we basically started to think about the benefit of being able to, and I want to apologize in advance, I've got 4 kids under 6, so there'll be a lot of noise in the background here and there, so, but that's okay, I'm sure we're all in that state at the moment. So this was our first step into this sort of multi-state fusion, and I'm going to talk a lot more about that because you can get a lot out of really being able to extract data from multiple sensor sources that can give you a lot better insight into the holistic performance modality for your, whether it be an athlete, warfighter, or any individual. So this is an example here where we use that tech as a way, for example, now of being able to monitor and ultimately optimize, for example, target acquisition with the warfighter. So you can see here on the right, a very sort of basic and baseline sort of GUI, and where we basically were able to monitor rifle trajectories and then ultimately tie that to whether the warfighter did or did not access the target. And you can see that this could be used as a framework both to monitor the performance post-activity, but ultimately these types of things can be used in real time to sort of use as a biofeedback model where you can actually optimize performance. So again, you know, these types of technologies, we've used them in a lot of different ways. And as I go through the presentation, I think that, you know, a lot of the work that we've done previously led us to what I'll talk about for the rest of the time, which as I said, is really being able to exploit some of the benefits of multiple sensor modalities in parallel. One of the biggest and most important things to consider in using wearable technology, which I'm sure those people that already do are aware of, is so wearable tech gives you a lot of high volume and nowadays high fidelity data, such as the iMeasureU sensor. But one of the most important things, as I said, is how do you take those multiple data streams that you can get and really distill them down into what I would call very digestible and translatable metrics. And this is one of the areas that we have a lot of expertise in, for example, where you really want to be able to develop a metric that continues to successfully inform performance or a performance outcome that's of interest to you. But also you want to do it in a way that it actually can be digested either by the athlete or the trainer or the coach, and so that they can actually use that in their training. And so that's one of the things that does take time, but we do have a lot of expertise in. And here's 2 examples where we outfit our simulated warfighters with different sensors, and we're able to actually predict performance based on a single metric. Now that metric may or may not come from one sensor, but again, it comes down to having a metric that really makes sense and that you can use, as I said, to inform success in terms of performance. So I wanted to spend the rest of the time and talk a little bit about this idea of what we do now at Exponent and how we use these sensors, and primarily the iMeasureU sensor as an example, where we really look at this interaction between human performance and sort of human product interactions in the wild, as we call it. and where you can use these types of technologies to really understand a lot of key interactions in a lot of different athletic or sports scenarios, and military scenarios, or a lot of different product scenarios as a whole. So again, the general framework is, traditionally, as we know, we tended to try a lot to bring the wild to the lab, where we would have our lab setting, and we would do as best that we could to simulate or replicate these sort of naturalistic movements in a lab environment. Now, in some cases that can be done, but as I'm sure you know, when we get into these more extreme scenarios, it's really challenging to do that well. But with the advent of what I would view as, improved high fidelity wearable sensor technologies that generate high volume data in particular, we are now really able to bring the lab to the wild with a lot of success. And so we focus our efforts on the right hand side, and where we use this sort of in the wild model to really support, through a generalizable framework, all sorts of products, all sorts of performance outcomes, and all sorts of different groups, whether they be athletes, soldiers, clinicians, or otherwise. So this is our overall framework, and I wanted to just talk about this briefly because I don't want to get bogged down in the weeds with this. But our basic model here is on the left, our baseline in the wild test model, where we basically incorporate different sensor technologies, and it depends on need, but we have a suite of technologies that we can pull from. And we then look at how those performance outcomes basically integrate with what we call the intersection between performance and perception. And so if you think about some type of activity, where it be shooting a basketball, or you're sort of making a route or taking a different route, and you want to understand not only how they perform, but how they perceived that performance to be. And by understanding that intersection between performance and perception, you're really able to provide an optimal experience, both in terms of the outcome, but also in terms of the athlete or the client or a product user, that optimal experience overall. And so if you think about it, what you do with this wearable technology output is you basically can then rank the metrics that you generate from these technologies in terms of how do they inform performance or product design. And so you get to stack rank those, and that's what goes back to what I talked about earlier in terms of being able to distill all the metrics down to the most meaningful metrics. And so I have a shoe here, but this could be an athlete, right? So these metrics can ultimately then improve production or improve performance. But the other thing about wearable technology and being able to collect data in the wild is not only can you optimize performance in the wild, but it also does something additional, which is also really important, where typically what you'll find is, and maybe most of you in the audience that do have wearable technology, it's more of a hybrid approach where you still will do your lab-based testing and you'll have your hybrid in the wild or field testing in parallel. But what the wearable data gives you is it actually allows you to improve your lab-based testing or simulations, where you're now using real-world product drivers or real-world data to adjust and basically optimize those lab tests. So for example, if you are doing some sort of lab-based treadmill training program, and you've been traditionally using certain speeds or speed changes based on what you read in literature or otherwise, now you can actually collect data on your own athletes and look at what the actual data are and then feed that into your protocols, so that your athletes or your warfighters are getting data both in the lab and in the field that are very synergistic, which is going to improve the performance outcomes overall. We focus and we function and operate within what I would call our data-driven performance continuum. And this is sort of where I feel as there are tremendous opportunities in any space of performance, where we're looking both at not just the execution of performance, but also in performance readiness. And what I mean by that is, so if you think about an NFL or a basketball player or a Major League Baseball player, they execute a task at a certain time. And that's ultimately what we're interested in, optimal execution. But optimal execution isn't just about that moment in time. It's also all of the readiness factors that go into being able to set them up to have that optimal execution. And what wearable technology allows you to do now is collect data on all phases of that continuum, where you can not only collect data during performance, but you can actually collect data in recovery, whether it be rehab or recovery, or maybe it's sleep data between bouts, where if you incorporate all this together, you can now ultimately come up with this sort of predictive framework, which allows you to determine, how do I basically optimize my readiness metrics so that I can ensure that I'm getting optimal performance execution on the day. And I'm going to talk more about that throughout the presentation. But we do this now, and we use wearable sensors to support all phases of this work. So this is an example, right? So wearable exploration of the performance continuum. We have our athlete in the middle, and we have a lot of different wearable tech that we can use, and we do use for readiness. So maybe that could be sleep data, it could be hydration, it could be load management, as we use with the iMeasureU sensor, for example. It could be foot pressure data over time. And then we can also then collect performance data, like I said. So it may be biomechanical data, it may be physiologic data, it could be a combination. And a lot of these sensors can be interchangeable on either side of that continuum, depending on your need. And I'm going to talk a lot more about how we do that. And so ultimately, this relies on, which is what I touched on at the start, really multi-state sensor fusion. And so if we're talking about an opportunity to start to consider multiple data streams to inform performance, which ultimately is critical if you want to get this holistic insight into your athlete or your soldier or whoever it may be, you really need to be able to fuse data that comes in from all these sensors successfully so that you can draw confident insights based on the outcomes. And it's somewhat non-trivial, but it's actually very achievable now in the current state of these sensor technologies. And I want to talk a little bit about first how we do that, and then I'm going to give you some examples of how we have done that and how we've used that to inform success. So, in a nutshell, so what we do with our sensor fusion model is, sensors such as the iMeasureU sensor, for example, will give you Unix time. So they'll give you a Unix timestamp, and without going into depth about what Unix timestamp is, it's basically just it's a global time. I think, if I recall, it started in 1970, where it's a time in seconds from that time point, and it just moves forward. So basically, if you can then map every sensor to that Unix time, it allows you to successfully basically synergize or sync across sensor technologies very easily. And we do that now. So we take, for example, the Unix timestamp from different technologies, we can sync them up based on that Unix time, and it allows us then to basically look at these different data across different technologies at the same point in time. So here's an example where we, for example, we've used GPS data and the iMeasureU data. We've synced the data across based on the Unix timestamp, and it allows us then to get a whole new range of data and insights out of performance that we weren't able to get before. And so it's as simple as that. You can then add additional sensors in using this same timestamp. You can pull explicit metrics from each sensor based on need. And basically, if you use this model, it's almost unlimited in terms of how you can think about integrating these data together, which is really insightful. So I'm going to give you some examples. So here's an example of where we took data fusion to the extreme. So as some of you may know, the extreme running or mountain running sort of culture is huge in Europe. And so this is an evolving area in terms of athlete performance, where it's very basically impossible, if you think about it, to be able to quantify athlete performance in a lab in this type of environment. And so we went and actually explored this in a very unique way. So you'll see there as an example, we actually compared an amateur, and that looks a little bit like someone presenting now. So I was the amateur, we had an expert, and we basically synced multiple sensors across a 6-hour ultra marathon through the Swiss and Italian and French Alps, and collected these data in parallel. And I think, if I recall, and maybe at the end James can talk about this, but this was the longest collection at the time for the iMeasureU sensor. Especially for the amateur runner, who took slightly longer than the expert, but we don't need to talk about that right now. So basically what we did was, using that sort of data syncing and that Unix timestamp, we're able to sync data across multiple sensors for that in total time. So, for example, a lot of sensors like the iMeasureU sensor have considerable onboard storage. So we're able, and a long battery life. So I think it's up to 12 hours. So we were able to collect continuous data over that entire 6-hour event. We also incorporated GPS into this as well. So it allowed us to really not only look at the overall performance, but by, for example, then fusing in GPS data, you can now start to localize your assessments and have additional considerations, for example, in terms of, well, what are the performance outcomes with this grade or that slope? What about in the more extreme terrain conditions? How did the performance change there? So this was just a very basic example outcome that we were able to draw from those data by fusing the GPS data with the iMeasureU data, for example. So you can see that if we just look at trunk sway between our amateur and our expert, we're able to glean very quickly there are some important differences between a novice runner in these sort of extreme conditions and an expert runner in terms of how much trunk sway is going on. And if you think about performance, where we want to really remove that unwanted and unnecessary additional trunk sway because it basically takes away from moving forward and performing successfully, this may be an example where you can intervene either through training, through apparel, through lots of different avenues to really reduce that discrepancy. And this type of information is something that is really hard to glean in a lab setting again. And so it allows you to really look at data longitudinally in ways that maybe we couldn't before, where you can really get some very important new insights into how does fatigue manifest in these types of scenarios as well. So again, another example where we then fuse in an additional sensor. And you can see that if we look at pronation velocities in the foot, for example, and now if we're thinking about how can we improve footwear, you can see some pretty important differences, particularly in the downhill. And as the amateur, I can tell you on the downhills that are really extreme, there's a lot of differences in the way that I would land and stop and start compared to an expert. So being able to fuse these data together gave us these very novel insights into where the differences in this metric are that could be addressed in maybe new shoe design and so on and so forth. So this is I wanted to talk about what I said about this data fusion. So here's an example of now where we incorporate the GPS data with the iMeasureU data. And it allows us essentially not only to look at instantaneous biomechanics, but it now allows us to contextualize those biomechanics. So looking at where someone is in space, in 3D space, or in the world essentially. So we can look at how do our trunk biomechanics or our lower limb biomechanics, how do they change on an uphill versus downhill? How do they change if you go up and downhill 6 times? If I wanted to look at a certain spot on that uphill, and because I know that there's a different terrain configuration, I can now hone in on that because I've been able to fuse these data sources together, and it allows me to do so. So if I'm thinking about, for example, and I want to apply this now in the warfighter setting, it's going to be really important if I know that, basically as they move away from base, and I know that there are certain terrain considerations to be made at certain aspects away from base, now I can actually look at how their biomechanics are sensitive to those changes in a very new way. This is another example of where we can use this. And so one of the other things that we do a lot is, and again, I think the other thing that's been opened up by fusing different sensor technologies together is it allows you to really develop a new set of metrics and think about new metrics as a way to inform performance and give insights that maybe we couldn't get before. So I'm going to give this as an example. So here we have a certain bike and we have different bike configurations. We have 4 different bike configurations, and we have 3 different riding considerations. So we have uphill, downhill, and flat. And by integrating some of these sensors together, and we use iMeasureU as one of the sensors here. And if you look at, for example, lateral lean and lateral lean velocity across these different considerations, you can see some pretty different heat maps, for want of a better word, so relationships between these particular metrics based on the 4 different bike configurations, whether we're going downhill, uphill, or flat. And if you think about, for example, now I want to design a bike that really optimizes performance for my rider, I can use this type of integrated or sort of fused data metric as a way to do so, where I can see, for example, configuration 2, and if I know, for example, that a bigger heat map or a broader heat map corresponds to what I would call ineffective performance because it's not allowing you to produce as much energy going forward on the bike, then I want to be able to reduce this type of relationship. So if you look, for example, at bike condition 2, in the flat condition, you can see that there's a much broader heat map compared to some of the other configurations. So it really helps you to be able to develop, whether it be an optimal product. But now if I want to apply this to training, I can do the same thing. So let's say I have a different training or a different sort of positioning I want to use, or a different athlete training program, and I want to be able to look at specific metrics. I have a new way to compare them using these wearable derived data that I couldn't before. That's my 2-year-old, he's hungry in the background. This is another example where you can actually take it to a bigger extreme. So now we add an additional sensor to our analyses, and we can start to look at not only how do those sort of heat maps broaden, but where is the intensity in that heat map. So if I want to, for example, think about an example where I want to get a certain degree of adaptability in my athlete, but I also want them to be able to hone in and be really, really precise at a certain stage in their performance or on the field, I can use these different sensor technologies to do it, where I can compare, for example, different cleat configurations in this case as an example, where I can look at, okay, cleat E is an example where I'm optimizing performance more effectively because I'm considering a lot more inputs rather than just, for example, speed. Now I'm incorporating specific biomechanical metrics. I'm incorporating particular trunk sway metrics. All these types of things can be brought together through fusing these data sources. So you don't only have to think about this in terms of an outdoor environment, because with advances in technology, and again, going back to the same sort of data fusion or fusing different data sources together, you can use it in different indoor settings. So this is an example of where we use the iMeasureU sensor, and we can actually look, and an RF chip, where we can actually now look at not only how does a person move within 3D space within the workplace, but when they perform this particular task, how do they move in those localized settings? And so here we've been using an example of where we've developed sort of automated movement signature detection algorithms. So we can look at, based on the certain movement, we can say, well, this is movement where they go from point A to point B, or they lift a box and move it to the second shelf versus the first shelf. And so we have that ability through fusing these data together to look at their local movements, but then also how do they perform these movements in this corner of the factory versus if they move to the other corner of the factory, maybe where it's a more constrained space, there's more noise, and so on and so forth. So again, if you think about incorporating an RF chip so that you get position, and then you also now add to that the iMeasureU sensor example, where you get local biomechanical data, you can again bring these data sources together. So if you think about RF chips in shoulder pads or whatever it may be, it gives you a way to contextualize your biomechanical data in a very novel way. And in doing so, I think it gives you a lot more insight into the overall performance of an athlete or a person in general. I wanted to touch briefly also on how we've done this with what I talked about earlier in terms of readiness and execution. So this is our sort of first example of how we've used for the iMeasureU sensor on both sides of that equation. So if you think about it, we use the cloud-based data that's derived from the iMeasureU sensor to give us some of these readiness metrics. So in this case, it's load management, right? So we look at cumulative load based on the cloud-based data in an athlete. Now in parallel, on the execution side, we bring out the raw data from the iMeasureU sensor, and we use those raw data to develop these specific performance outcome metrics. So whether it be joint biomechanics, it might be impact loading, it could be trunk sway, or it could be a combination of these things based on whatever our performance need is. So if we use this relationship, we can use a single sensor here to get data on both sides of the equation. And then based on these performance predictors, and using some basic data analytics, we can actually come up with an optimal set of performance sort of readiness predictors that go in to infer the success of the performance outcome. And once you have this model in place, you can then start to think about how you want to play around with or change or optimize these readiness data so that you can actually optimally have your athlete perform optimally on the day. So for example, if we use this as an explicit example, we can use the load management data where we can see that on days where they loaded more regularly or higher, or if their cumulative load was higher, their performance was down. And so we can continue to adjust the load on recovery days to make sure that on the day of performance, they're optimally ready to perform. And so this is a nice way to do that. And you can use the wearable data on both sides of that equation. Now we've taken this a step further recently, where now we've incorporated some specific sleep and recovery metrics into our performance predictors. Now, again, if you think about it, now we're not only getting some of the load management data from an iMeasureU sensor, for example, but we're also now getting some important sleep, heart rate variability, resting heart rate data, which when you combine it now, you're basically coming up with a scorecard, a report card, which says, you know, based on the fact that between bouts, so let's say I'm talking about a basketball player and they play every third night or every second night, I want to look at what they're doing between games. And so I can collect these data continuously on the left-hand side, and I can then relate that to their performance. Now, it may be sensor-based performance, or it may be, for example, their overall performance gauged on points scored, rebounds, etc. These data on the left are a way to really hone in on how do I optimize their performance success by measuring these things continuously. Now, it's obviously challenging because when you talk about executing a performance, that's usually over a constrained time period. So it might be an hour, maybe 4 or 5 hours at most. So it's pretty easy to collect raw data in that case and then go through all of those raw data to pull out explicit metrics. It's a little bit more challenging on the left-hand side where maybe you're collecting data over a 4 or 5 day period. So it really is up to the way you design that experiment or design your study as to how frequently you want to pull data out that goes into this analytical model. But again, once you've come up with that sort of relationship, this is a really unique way of being able to basically determine what metrics are improving performance, or which metrics is performance most sensitive to, and then you can start to adjust these a great deal on the left-hand side. So, you know, another example of where this can be applied, if I think about the warfighter setting where soldiers are continually moving, not only in time zones within a country, but globally. And if you think about the fact that in those changing time zones, sleep's going to change drastically. So if I can start to get insights into what are some of the sleep metrics that directly infer performance, then maybe I can start to think about targeted sleep modification programs. Maybe it's things about circadian rhythm adaptation or so on through light therapy is a very sort of extreme example, where you can actually adjust and modify the sleep profiles to basically have that warfighter ready to perform optimally on the day. Now, obviously, this type of work it's in its early stages, but I think this is where there is huge potential in this combined wearable space, where again, as I said at the start, not only are you thinking about monitoring performance execution through wearable technologies, which is typically the way we've viewed these types of technologies being most beneficial, but now you can actually think about using them in a whole new way where you're actually monitoring what I would view as equally important metrics that go into this whole performance continuum. And that's sort of where we're at right now in our work, where we basically like to explore this whole dynamic. And through our fusion methods that I talked about, we basically the sky is the limit in terms of how many metrics we want to bring in and explore. So to touch on this as a final sort of slide, I probably talk way faster than I should, so I apologize, James and Blake, for that. This is our overall framework, right? So if we talk about readiness, you have lots of different technologies that can go into that. I talked briefly on perception, but again, there are technologies that you can use to understand and integrate perception. And then you have execution. And so I might have products here, but this could be an athlete, right? So I basically, through this relationship, I can really improve and innovate in terms of the way I train my athlete or improve performance based on this continuum. I can also, through this relationship, come up with new ways that I may want to train an athlete, or maybe it's develop a new product to support that training. But in parallel to all of this, I'm actually directly supporting the athlete through all these data. So the fact that you're giving the athlete, the coach, the trainer, all of these data, and again, the challenge is being able to distill it down into metrics that make sense. But through this framework, you're actually able to give a much more holistic insight into how do I best optimize performance for my athlete or my person, warfighter or otherwise, by considering all of these different factors. And what I think is great is each facet of this relationship can be achieved through a wearable technology. And I'll go back to what I said at the start. You know, there are technologies such as the iMeasureU sensor, which are high fidelity, provide high volume data in all sorts of capacities. And I think, again, what I like is when you have sensors that can give you both raw data and a cloud-based offering, that's ideal for us, because quite often you want to be able to really pull those raw data and come up with new ways to consider them. But I think we are in a position now with wearable tech the way it is, where we have we're at the forefront of being able to really explore optimal performance and performance optimization in a whole new way that goes above and beyond what we've done in the past. You know, I think that we are now able to extend well beyond the lab and go into the wild much more readily and more consistently, and provide data that's probably, in my opinion, much more beneficial to improve performance moving forward. So I wanted to thank everyone for their time. If you do have additional information or questions, you can please reach out to anyone here on the screen. As I said at the start, we view ourselves more as the data experts or the study design experts in parallel with the data. And we like to partner with iMeasureU because we view them as a technical expert a lot. So I think if you have questions on either side, please do reach out, as I said. And thanks so much for your time.
Thanks, Scott. We do have some questions that I'll ask you in a bit, but just to remind everyone, if you do have questions you want Scott to answer, we do have a bit of time, so just enter them in the Q&A section, and then I'll read them out loud. So Scott, the first question is from Jesse. He says, thanks for the presentation. Obviously, there's a plethora of metrics each tech gives you. What's your process for establishing what's important for design performance?
Yeah, that's a great question. And I think The key is always to make sure that the metrics that you come up with directly relate to some important performance outcome. I'm going to give you a very simple example. So if I'm talking about a 100-meter sprint, I know my performance outcome is to run faster and so have a lower time. And so I want to make sure that any metric that I'm measuring, I can relate back to that performance outcome. Otherwise, you know, you can get off track in tangents in terms of pulling metrics in that maybe don't very easily inform success. So that's the first criteria that I have. The second one that I have, again, is this metric something that you can actually change easily or can be digested easily to be changed? So again, if I use the 100-meter sprint as an example, and I decide that the metric that came out as the #1 ranked metric is tibial, let's call it tibial rotational quiver, for want of a better word. And it's a metric that says, yep, every time this is the metric that tends to be closely related to performance, but I know it's something that I can't really train my athlete to a change, or it's something that's going to be really difficult to change, then it's not something that I prioritize in my measurement. It might be a metric that I measure and look at and give the coaches data on that. But again, it needs to be something that can actually be modified, particularly when I'm talking about performance. Otherwise, it doesn't carry as much weight in terms of the way we put things together.
Okay, and I think this question is a follow-up to that. How large are the data sets that you end up compiling with the various levels of data, and how do you deal with digesting those massive data sets to find those MVP metrics and variables?
It's a great question. So it really depends on the activity. And again, if I go back to our extreme mountain running, as you know all too well, James and Blake, that was a huge volume of data, 6 hours of continuous data. And sometimes you're talking about multiple data streams. So, you know, we've learned with experience along the way. It can be challenging, but I think the way we tend to deal with that is we've developed a lot of sort of processing tools in-house to basically pull out explicit peaks. And this is what I would say as a first pass at that. And it does go back to the first response I had, is knowing in advance what, you know, you tend to hypothesize based on what metrics you think may be important. And that's something that you can do. And I think one of the things that I have learned is to really value the input of a coach or an athlete into what those metrics should be. For example, no one knows more about, you know, if I'm talking about how do I improve throwing a football from a quarterback, I can sit there all day and talk about velocity and speed, but the first thing I should do is talk to a coach and say, what do you look for? What are the things that you know seem to be most important in a performance outcome? And let's say it's elbow position at release. And then so what I want to do is then go in and go, okay, so I want to look for certain points in the data that I know will relate to these metrics that I think are the ones I should be exploring. And we do that up front. So then it allows us to really go in and stream through the data and pull out those explicit points as a first pass. It helps in really consolidating our processing sort of methods. And then from that, we do tend to go in and explore different components of the data. You know, with computational speeds the way they are now, I will give you a great example, right? So we batch processed recently 20 subjects of data at 4 hours per subject, and it took a couple of days of computational time to do that. But again, you know, we basically set up those metrics in a way where you can start the computer and walk away. But it really does depend on what question you're asking. As we've moved more and more into those multi-state metric considerations, it does take more time. But I think, again, you know, the ability to do that is very viable now. But I can't stress enough how important it is to really have realistic hypotheses up front in terms of what you think the metrics could be, and make sure, as I said, that they do relate to a viable and measurable performance outcome.
Okay, thanks, Scott. So what would you say if you are interested in starting this concept of sensor fusion? What would be your first step?
Yeah, I think first step is to take a high volume or a high fidelity sensor. So that's why we started with the iMeasure sensor. And I really think that something where you can actually, okay, I'll take a step back. I think what we've gained the most insight from is by linking it to some sort of geo-tracking sensor. I think by contextualizing the localized mechanics has helped us a great deal in understanding performance. And so linking GPS, for example, with the biomechanical data has given us a lot of valuable insights, and it contextualizes, as I said, the performance. So it's one thing to be able to say that, for example, my trunk sway or my knee angle is this, or my tibial acceleration profile is this. But it's more valuable when I can say, well, actually, it's this because they were running uphill and it was this and it was that. And I can now pull in those additional data. So I think as a first pass, lowest hanging fruit is usually to sync in GPS data because it's easy to do. It's relatively seamless using the Unix timestamp, and it's highly valuable in terms of insight. And that's easy to do when you're outside. If you're indoors, I think, like I said, we've done the RF chip. It's a little bit more challenging, but it can be done. But I think probably that, and in parallel, there's a lot to be gained by thinking about, and I didn't show too much of it here, but fusing a physiologic and a biomechanical sensor has been really valuable because these two things go hand in hand, right? So quite often if I think about even mechanical load or work, you know, the biomechanics basically dictate how much work that athlete's doing. And if they have suboptimal biomechanics, then it's going to be able to presenting itself in the physiologic outcome of work. So if I, for example, as simple as something like heart rate, can be great, but now if I want to think about syncing muscle oxygenation with the HUMON sensor that we've used, or if I want to think about resting heart rate or heart rate variability, fusing those two metrics together can be equally valuable because it allows you to understand the physiologic component as a result of the sort of biomechanical performance. And again, if you go back to talking about a viable performance outcome metric, it might well be that your outcome is, I want to improve the physiologic work of my athlete. I want to make them go longer. And so I'm going to have a metric that measures that ability to go longer, fatigue or otherwise. And so now I adjust my biomechanics knowing that I want to improve that outcome.
Okay, great. So this question is from Irina. She says, have you applied this concept of readiness and execution continuum and wearable sensors to elite professional dancers? And if not, how would you start?
It's a good question. I have not, and I am not an elite professional dancer. But how would I start? I mean, I think the way we approach this is everyone is an athlete, and what I mean by that is you can be a patient in a hospital, you can be a warfighter, you can be a shopper in a supermarket. The goal is always to optimize the experience and the performance. So if I talk about it with a professional dancer, and I think about the fact that, so what's unique about a professional dancer, and again, I'm not one, is the fluidity of the movement, right? So it's not just the localized biomechanics, but the flow and the apparent fluidness or the smoothness of a movement. So thinking about how can I measure that smoothness, and I can do that with a accelerometer, and I measure U sensor, for example, where I can look at jerk, movement fluidity, intersegmental interactions in terms of dynamics. So I can use that as my sort of biomechanical data sensor, and I may want to then, as I said, talk about a physiologic sensor where I want to be able to maintain posture and maintain performance for a long period of time. Or bringing up the word posture, maybe you want to add, for example, an additional sensor that allows me to understand general body posture. I think when you're talking about performance in an athlete, which is primarily biomechanical, there are lots of different biomechanically driven sensors that you could bring together. So for example, we use the iMeasureU sensor a lot for some of those. We actually use it a lot for upper body dynamics as well. But then if I'm talking about localized foot data, maybe I want to bring in a foot pod type sensor and take the benefit of that sensor. So, when thinking about fusing sensors together, we always want to make sure we exploit the maximal benefit, or what are the highest fidelity metrics that each sensor brings, and make sure we exploit those in our overall paradigm.
Okay, great. We're getting a ton of questions, so I probably have time for 2 or 3 more. All right, so this next question is from Irene. She says, I'm wondering which technology apps for monitoring sleep have you found to be the best in fusing with IMU metrics?
Okay, so this is what I've found so far. I mean, there are lots of, and I'm not trying to give plugs to different companies, but I'm going to be honest. There are lots of different ways to measure sleep out there now. Quite often, you've seen the wrist-based trackers will quantify sleep, but the one that we've used most extensively recently would be the Oura Ring as an example. The ring-based, and there's a couple of reasons why we do that. One is, again, sleep is really, and being at Fitbit, I'm aware of this, sleep's really hard to track. It's really hard to measure accurately because you get a lot of movement artifact on a wrist-based tracker, for example, through the night. but the ring is great because it's fixed to a localized location. It's unobtrusive. It gets some really high fidelity data. And not only does it give you really good sleep data, but it also gives you a lot of those underlying physiologic recovery metrics like HRV, resting heart rate, which we've found to be really useful. And the other one that's great about it, like that, is it gives you temperature and respiration. So we found that one to be useful, and we are using it and implementing it more because it not only gives you, like I said, really good sleep data, but some really great additional physiologic metrics that I think are critical. And it's relatively straightforward to fuse in with the biomechanical data. A little different because, you know, it's not continuous per se, but you can glean out those metrics now in a pretty simplistic way and relate them to the more continuous biomechanical data.
Okay, probably have time for two more. So this question says, team sports, for example, basketball, are obviously more chaotic than endurance type events in sports. How do you determine key performance outcomes in these settings where physical outputs aren't necessarily the most important?
Yeah, it's a good question. Basketball is a great example too, because I talked a little bit before about, you know, contextualizing the movement. And if you think about basketball, where most of the arenas will have the ability to either have cameras in there already, or you have ways to be able to track player position, I think by fusing that data in with these localized data is a great way to make that starting point. But again, it goes back to what I said before about, and I agree, you know, it's not so much about how much you move during the game, but it's usually rebounds, blocks, it's shots made, shots versus shots attempted, you know, general stamina throughout a game. So I think, again, tying your performance metric, so maybe, for example, in this case, it's more of a physiologic metric, or maybe it's more thinking about that readiness execution paradigm that I talked about, because the other thing to touch on is, you know, I appreciate there are some sports where incorporating wearable tech is challenging because having athletes wear those techs during a game can be problematic, or it's something that isn't going to be done. So I think it's, in that case, it's within basketball as an example, it's coming up with the performance outcome metrics that you can easily measure in a game, and maybe tying that in with some of the position data, because you can get information on how far they move during a game, and you can compare that from game to game, knowing that, wow, in this game they didn't really go as far and didn't travel as much distance over the game, and that was related to their outcomes. But now I'm bringing in some of those wearable sensors in rehab, so load management, maybe it's sleep data, maybe it's in the readiness stage where you can bring in those additional metrics. Man, my kids are getting loud.
All right, probably last one. When looking at optimizing warfighter performance, who are considered key stakeholders in determining primary outcomes, and what are the most actionable data findings are? What does the composition of the team look like compared to a sports setting?
That's a good question. I'll try and answer it as best I can without things I can't really talk about. But so essentially, I think who dictates what those outcomes are, I think it really depends. And as anyone knows, in the military space, there are a lot of different groups, different sectors, and all have very different needs. But if I'm talking about supporting, you know, the critical, you know, the warfighter readiness, performance readiness initiative within the military, I think most of the things that we target and have worked with have been about performance degradation. So, you know, you have certain tasks that you want to achieve for a certain amount of time, and you want to make sure that you can help the warfighter maintain that level of performance over an extended period of time, knowing full well that they're going to be going through some pretty arduous scenarios. So a lot of the time when we use the sensors in that case, it's more about movement consistency or biomechanical data consistencies over time, and at what point, and this is, you know, this has been talking to different commanders, etc., at what point do we start to see a fall off in those metrics? Because that's really important, not in terms of just performance, but also the safety of the warfighter, or the group of warfighters in general. And so we tend to focus our efforts around that. In terms of the question about the team, I'm trying to understand what that meant. I think if you mean the team that we work with, we tend to typically work with the biomechanists within the military as well. I mean, you know, we've worked with NATIC previously, with the Solar System Center there. We work with other groups now in a similar way. But, you know, I think it's actually what we tend to try and do is partner a lot with the biomechanists in-house, whether it be sporting populations or military populations, because, you know, working together and collaborating across those continuums is they provide a great bridge between the tech and also the data side that we provide. And so we do that. And in terms of our own internal team, it doesn't change that much. I mean, it's, again, we approach everyone as an athlete, warfighter, patient otherwise. And when you do it that way, you're doing two things. You're optimizing performance, you want to maintain it, and mitigate risk. And that's what we use the wearable tech for as a whole.
All right, thank you, Scott. And thank you for the excellent presentation. Sorry if we weren't able to get to all of your questions specifically. Feel free to reach out to Scott, Blake, or myself if you have any follow-up questions. And thank you everyone for your time. We'll be emailing this webinar in about 24 hours after it's all been processed. So thank you.
Thanks very much.